Good morning, guys. Today we're going to go over Chapter 3 of Physics 101, which is vectors. If you haven't heard of them already, vectors are a very important topic in physics, and you will also see them in calculus. Usually, calculus 3, you start talking about them. So let's go right into it. Before defining what a vector is, we're going to start by defining scalars. So, the definition of a scalar is the following. It is an ordinary number such as real or complex numbers and that's it. It's literally a normal number. And a few examples of scalars are the following. You have mass, we have temperature. These are all just numbers, right? No direction, it's just a number that represents something. Temperature, density, charge, among many other, right? Energy as well, I'm gonna write that one because energy is something that we're gonna deal with a lot in this class, right? And usually scalars are usually used, at least in these situations, as the strength or the amount of each quantity. So I'm just gonna write strength or quantity or amount, right? So like mass, there's a certain amount of mass. We're gonna give it a number to just let us know how much there is. Temperature, same thing. And that's pretty much it. It is important though to realize that not all measurements or physical quantities can be represented by scalars. Some quantities are vectors, right? And that's why we only have a set number of examples here. There are a few others, obviously, there's countless others actually, but a large number of measurements and physical quantities are actually vectors, which is what I'm going to spend the most of today talking about, right? So let's get into that. Erase that. Erase that. We're going to write vectors. Vector. Okay? So it is a directed line segment. Okay, right? And we're gonna add a few arrows here just to give some extra details. It has a direction or orientation, and it has a length or magnitude. We're usually going to speak of magnitude. All right. And usually we represent these with arrows. So the magnitude is, or basically the length is, if we represent these geometrically, is going to be the length, right? So this is the magnitude. And then when we consider the angle, that is the orientation, right? It's where we're pointing. And the magnitude is how hard, or with what length we're pointing. So, a few examples of quantities that we can represent with vectors are the following. We have position, velocity, acceleration. We have force, momentum, all of these, right? So we have quite a lot of physical quantities that we can represent with vectors. Yeah, and so the magnitude, as I was saying before, just designates like the strength or amount of the quantity, while the orientation represents the direction of that quantity, right? And usually we have like a convention for naming these vectors, right? So if we're talking about the vector A, we're going to usually put a arrow over its head. That's how we do things. That's how we represent vectors with a letter. And usually the magnitude of the vector is written like this, right? Though in a lot of physics classes, usually in physics classes, people end up just not, if they're talking about the magnitude of a vector, wait, hold on, let me just write this. Magnitude of A. Yeah, so usually people will end up just writing A when they're talking about the magnitude of a vector, right? And that's it. It's worth noting that now that we've already gone through this, we know that we can represent the orientation of a vector with theta, which is the angle that it holds, right, with respect to the x-axis. And as we do some more practice, that's going to be a lot more understandable. Before we continue, another noteworthy point is that vectors are equal. I'm going to draw some vectors, and I'm going to point out something about them. We have this one, we have this one, we have this one, like that, like that, like that. Okay, now what do these vectors have in common? Well, actually, they are all equal to one another because they have equal lengths and point in the same direction, right? So, equal lengths and same direction. Some of you might be confused with that statement. Length, sure, like they all have the same length, we can measure that, but direction, what? They're pointing the same. Oh, they are pointing in the same direction. And the reason for that is that if we were to draw parallel lines parallel to the x-axis, and we measure these angles, we would see that all of the angles are the same. And thus, we're dealing with the same vector many times over. Now we're going to go into how to represent a vector, right? How to write the coordinates. Yeah, and this is going to start being a lot more relevant to us in the physics world. So there's two ways to represent a vector. There's the polar representation. Which we're going to start with. So this one uses two scalars. We have uses two scalars, magnitude and orientation, right? So the way that we actually represent a vector with polar representation is the following. So we have a vector v, which is equal to its magnitude, comma, its angle. And that's pretty much it. That's how we present it. And like for the sake of this example, you can say 50, let's see, 5.8, comma, 31 degrees, right? And there we go. We have a measurement of a length or of magnitude, right? And then we have the angle that the vector makes with respect to the x-axis. And this vector would actually look like this. Y, x. I'm actually going to measure 5.8 centimeters, even though we don't know like what unit this is. And we're going to put an angle of 31 degrees, right? So this 5.8. There we go. And this is the vector v. That's how we would represent it. Now, it's worth noting that this could be in degrees, or radians, and that this number over here, because it's a magnitude, it has to be positive. So we'll write always positive. All right, so that's how you use polar representation. And there's yet another way to represent vectors, right? I personally enjoy this one a little bit more, but you're going to use both. You have to use both. They're both equally as important. The reason I like this one more, the following one, the one that's about to come more, is because it helps to decompose the vector, and for some reason I enjoy that a little bit better. So this one is called the Cartesian representation. Right? Representation. Take a ruler to underline that. Oh. Bam, okay. Cartesian representation. And again, we're gonna have two scalars, right? And the first one is going to be the x component. Right? And the next one's going to be the y component of the vector, of course. And that might be a little bit like weird to you. You might be asking yourself, what is that? Well, it's basically each of these is the distance of the vector along their respective axis. It's along y-axis, right? So basically, if we had a vector, which I will be drawing right now, okay. Three, 5. Okay, so as you can see, we have a vector, right? This one's going to be called v as well. And we can actually break this vector into two pieces, right? We can have the magnitude of its y component, and we can have the magnitude of its x component. This one is equal to 3, and this one is equal to 5. It's literally the height and the width of the vector, or however you want to see it, right? And the way that we write that is the following. V equal to this, comma, this. Actually, I'm not going to write the little, yeah, well, we could. Right, so we have basically both components here and equal to 5, 3. There you go. Oh, actually, it's not 5, 3. This is 3, 5, as we are dealing with x, y, and x is 3, y is 5. So there you have it. Another way of writing it is actually with I and j. And here you're going to have to add them. It's a little bit odd. I and j. So it's like an I with a little hat. It's basically like the variable for the component that's with x. And then here we have the variable for the component that's with y. And if we had a z component, we would be using k. And we don't have one here, so we're not going to be dealing with that. Okay. And so why do we have two ways of representing vectors? The main reason is that we actually have ways to jump from one to the other. And this can help us in a number of ways. If you don't have, without having as much information, you can jump to many more conclusions with the help of these formulas and conversions, right? So conversions between representations. Okay. Okay, so the first one is basically the following. And we also have all right. This is for polar to Cartesian. All right, so say we have polar values, right? So polar being the magnitude of v, comma, its angle with respect to v, to x, I'm sorry. This is more like the x, y components. All right, so if we have those, we can take the magnitude and multiply it by the cosine of the angle with respect to x. So like this, right? And it will give us this value, the x value, the x component of that vector. And if we take sine of theta, we get the y component. And that's as simple as it is. It's quite a useful formula. We're going to be using it a ton this semester, right? So, yeah. And in case you are interested in why this formula is the way it is, well, it's because, see, if this is a, right? This is the, magnitude of A, and then we have an angle here. Then if you think about what the cosine is, right? And imagine we call this A of y, and then this A of x. then if you think about what the cosine of the angle is, it's equal to the adjacent side over the hyperbole, which is this. And that's it. You just swap sides, and then you have a formula you can use, right? Pretty simple. And this formula will come plenty handy. And the same thing goes with sine of theta, only that it's the opposite side over the hyperbole. Hypotenuse. I said hyperbole, I meant hypotenuse. Okay, so, and that's pretty much it. The one thing that we need to make sure that you do is that when the angle must be with respect to x, right? It has to be with respect to x, and usually you want it to be positive. So in the first quadrant, usually in first quadrant, unless it doesn't matter, say like the cosine, if it's negative, if we have like a negative theta and it doesn't really change anything if it's on top or below, it's because it's a cosine. I'm sorry if that sounds a little bit weird. Well, you'll probably see it in future problems that we're going to work on together. For now, let's go and take a look at the last, I think is the second last formula. If we're going from polar to Cartesian, we can find the magnitude of the total vector, like so. Right? So, in case you're wondering what this is, well, it's basically Pythagorean's theorem. Pretty much it. Like I said before, magnitude is this. And if we just took this root, if we squared both sides, we would have this squared plus x, the x component squared, plus the y component squared, which is Pythagorean's theorem. It doesn't need to be explained any more than that. And finally, we have this. Which is really a cool formula to use. Not too complicated, but cool. Basically, the arctan of the y component over the x component will give us the angle, right? But we need to be careful because often our calculator will not give us the theta that we're looking for, right? We want the theta in the first quadrant. That's what we usually want, unless we're dealing with an odd situation. Well, actually, no, sometimes we won't. It depends on the situation. The theta that we want depends on what situation we're given, but sometimes we're going to have to add, sometimes must add or subtract 90 degrees or 180 degrees, right, in these scenarios. And you'll see those scenarios come as we go along the semester, right? Finally, now that we know what vectors are, how we can represent them, and the ways that we can switch from polar to Cartesian, we can actually do some vector arithmetic. Very important to understand. Arithmetic. Just double checking for a second. I thought there was an A there. Okay, vector arithmetic. So we're gonna go over here right now. We're gonna go over adding, subtracting, and multiplying a vector by a scalar, right? There are many more operations, but for now we're only going to be concerned with those ones. Later on we're going to learn how to do a dot product, a cross product, and yeah, I think that's actually it for this semester. I don't think that there's many more operations that we can learn, but for now that's going to be it. We're going to start with addition. Right? So let's take vector v plus vector w. Okay, and there's two ways to do any of these arithmetic operations, right? The first one, we have two options. We have the algebraic way. We have algebraic addition, or geometric addition. Okay, so the first one is algebraic addition, which is what I really prefer, to be honest. The first thing that you want to do is express for this choice. The first thing you want to do is express vectors that you want to add in Cartesian. I'm just going to write Cartesian. Representation is the next word that I would want, right? We're too lazy. And then we were going to want to add the x components, and then we're going to want to add the y components. I'm separating these two steps to just show that you don't add x to y and y to x. It's really just x and y and y, right? And an example of this would be the following. Say you have v and w, and they are 5 and 3 plus -3 and 4. Well, then you're basically going to be adding the x components and the y components, which would give you 2, 7. Okay, and that's pretty much it. It's very, very simple. As for geometric addition, there are a few steps. I'm going to write them out just to make sure that you don't make any mistakes. Place the tail of W on the head of V, and part 2 is to connect the tail of V to the head of W, right? And so an example of that would be the following. So you have V, right? And then you have W. Okay, you want to add these two? Well, you place the tail of W on the head of V, as so. And then you connect the tail of V to the head of W. I drew it a little longer so you can see, but it's supposed to touch at the tip. This is how it should have been. See, they're colliding a little bit. And that's pretty much it. That's V plus W. That's literally V plus W. And that's it. All right, the next step is to learn how to do subtraction. Subtraction. A little bit more difficult. Subtraction. Okay, we're going to do V minus W. Subtract and then subtract. The algebraic subtraction is the same as the algebraic addition, with the only exception that you're, instead of adding, you're going to be subtracting, and that's pretty much it. So for this same given situation, imagine we swap this with a negative. Well then, let's erase this and go over it again. We would basically be doing 5 minus 3, comma, 3 minus 4. And what do we get? We would get 8, comma, negative 1. Right? And that's it. And then for geometric subtraction, again, we would place the tail of W on not the head, but the tail of V. Okay? So let's start and do that. Let's erase this. This is no longer the step. I'm going to erase this too. Say we have V and we have W. Place the tail of W on the tail of V. Okay, so it's going to look something like this. All right, and what's the second step? Well, the second step is to connect the head of W to the head of V. And it's very important that we choose these, that we listen to these instructions word by word, as if you swap V and W, you will not get the result that you're looking for. So connect the head of W to the head of V. Since we're connecting this one to that one, it's going to look like this. W minus V. And that's it. Another way of doing this is will require scalar multiplication, which is our next topic. We're going to do that right now. Arithmetic with vectors is fairly easy. It just takes a little bit of practice to get into the mojo of it. From that point onward, it's pretty easy. Scalar vector multiplication. Okay, use our ruler to finish that line. Okay, so we again have two options, the algebraic method and we have the geometric method. Bam. Okay, so when we're doing the algebraic method, if we take, say, V of 1, 1, and we want to multiply it by 2, right? We're multiplying a scalar. Well, the vectors be multiplied by a scalar of 2. We can basically write that like this, comma, 1, and then literally distribute the 2 on each component. And if we did that with a negative, we'd end up with this. 1, 1 is equal to negative 1, negative 1. We distribute the negative 1 over each component. And so if we had a vector of V like this, then this, hold on, this would be 2V, and then this would be negative v, right? So negative v literally swaps. That's how, if you multiply a negative number times a vector, you literally change the orientation by 180 degrees, right? And when you multiply a scalar times a vector, you just multiply that value times its components. Meaning, usually you basically affect the size, the magnitude of the overall vector, right? And that's pretty much it. And yeah, so another note, I was speaking about subtraction before. If we were doing w minus v, you'd say this is w and this is v. If we wanted to find out how to do it, we can actually turn this into an addition. This is actually my favorite way of doing vector subtraction. You take w, the vector w, plus minus v, right? So we have w, and then v, if it turns into a negative, would be like this. Same magnitude, only pointing in the opposite direction. So, and when we add these up, we end up with this. So we have w, and then we literally add it to this. Negative v. Put that over here, negative v. And then you just trace as an addition. W minus v. And if we were to do it the old way, the way that we learned to do it, then we would place the tail of w on the tail of v, right? Which would give us this, something like this, right? Yeah. And then we would connect the head of, we would actually connect the head, in this scenario, we would connect the head of v to the head of w, which is like this. Sorry if that's a little bit difficult to see. W minus v. And you see they're very similar. I'm playing with a lot of errors. Like I'm not measuring my vectors perfectly, but you can see that they're pretty much, they're very similar to one another. And if we were using actual values, they would be identical. And that pretty much summarizes the vector chapter, chapter 3. In any case, I really suggest you guys to just do a lot of practice with vector arithmetic and conversion between polar and Cartesian representation. Otherwise, I'm sure you guys are going to do fine with this. Thank you so much for watching, and I'll see you guys in the next one.